All right, let's go ahead and get started, man. Let's jump right into this. So we left off at network components. I think the last thing we talked about was a firewall. So now we're going to talk about what an access point is. So remember, we're in the network infrastructure. These are our network components that we're going to have to manage, maintain, and troubleshoot. So wireless networks, a big part of being a network engineer, network admin, is setting up, doing wireless surveys, setting up the access points, configuring lightweight access points, or cloud-based access points now with like Cisco Meraki. So an access point, at its base, does one thing. It sends out a Wi-Fi signal so that Wi-Fi enabled devices can connect to. That's at its base what an access point does. And then that access point takes that Wi-Fi enabled device and gets it connected back to our backbone infrastructure. Our distributed network is what we call it in like wireless vernacular, which is our wired infrastructure, right? A switch or a router. We have different types of access points. Now remember, at the base, that's all it does. Radiates a Wi-Fi signal in the 2.4 gigahertz range, and the 5 gigahertz range, and now the 6 gigahertz range. With this one having 22 megahertz channels, this having 40 and 80 megahertz channels. That can also do, that's a horrible 8. Hold on, let me fix that. That can also do channel bonding, like up to 160. And then 6 gigahertz is the same thing, right? We're just going to put up to 160 gigahertz, okay? At its core, that's what it does. Now, access points are not all built the same. We have 3 different types of access points that we're going to go over in the CCNA exam, and really that's the only types of access points there are at a high level. So we have autonomous access points. We have lightweight access points. And we have cloud-based access points. Now, these two are very similar. Just how we deploy it, how we manage, and the where the infrastructure sits is obviously going to be a little different. But first, let's go over an autonomous access point. So an autonomous access point, it does everything. And what we mean by that is this access point is going to be our router. It's going to be our switch. It's going to be our DHCP server. It's going to point us or be the DNS server. It's going to be our firewall, while also doing its base function, which is emitting a Wi-Fi signal on the standard ranges for Wi-Fi enabled devices to connect to. Typically, we see autonomous access points in small office, home office networks where you have the wireless router is what someone would call it, connected to the modem, or it could also just be a modem in there as well. So it's an all-in-one functionality, right? An autonomous access point does it all. And this will typically just be directly connected to your ISP. Of course, we could have a modem in the middle, or it could be like combined right there, right? That's an autonomous access point. Now, there are some scenarios where we can scale this a little bit, where we can have what's called a mesh network. We have this autonomous access point radiating a Wi-Fi signal, and that Wi-Fi signal is going to have what's called an SSID, a service set identifier that identifies a wireless network. An SSID identifies a wireless network, not an access point. Different. So we can have our SSID home here, and then in your house, you could go buy like a little extender, right? That's my Wi-Fi extender. I'm not the best, artist. But here's our Wi-Fi extender that could also be in kind of this mesh here, where they talk to each other, and then this broadcasts the same SSID. So we would call this a mesh network, where this now is a part of this autonomous access point network, okay? And they're meshed. Now, again, this is not highly scalable, because when we want to manage anything within this network, it's in the access point, right? This access point may host like a web portal that you access via HTTP. And if we need to manage this, it's also going to be in its own web portal. Not only that, with Wi-Fi signals and all RF signals, we get interference. So with like 2.4 gigahertz, we have channels 1, 6, and 11 that are the non-interfering channels. But if we're just popping up autonomous access points all over the place, we're going to get a lot of interference because we don't have some central way to manage all this, right? So where that comes into play when we need something more robust and highly scalable is going to be lightweight access points. I'm going to describe what a lightweight access point is, and that's going to lead us into cloud-based, how it essentially does the same thing, except the controller now sits in a cloud service or a cloud solution like Cisco Meraki. So a lightweight access point. Here's how a general design would be for our campus network on a collapsed core topology. So let's say, I'm going to do a little bit bigger here. We have our distro switches here. So these are our distribution switches. Okay? And sitting on that distro switch is our data center rack. So we're going to have our web server farm or our servers sitting here. Okay? And then we're going to have our access switches. This is where we're going to be all of our endpoints connect to. Okay? Maybe we have some redundancy here. So this is our distro / core layer. This is our access layer. Now let's say, again, this is small design, but let's say we have 1,500 users. And these 1,500 users are in a 6-story building. That's, let's say, 16,000 square feet. Okay. Can we use an autonomous access point here? Obviously not. So now what we have to implement is a lightweight access point. So our lightweight access points, I'm going to draw them in green over here. They're going to be controlled and managed by what's called a wireless LAN controller. So that wireless LAN controller typically is going to be sitting at this distro layer connected to our more robust switches, right? So let me draw that out here. So that wireless LAN controller is going to be doing the provisioning, the managing, the deployments, and where we're going to be doing most of the troubleshooting, right? when it comes to like our Wi-Fi profile, our wireless profiles for all of our lightweight access points. And this wireless LAN controller is going to onboard these access points, push their configuration, and manage them or push their profiles. So now the lightweight access point, we had that scalability where we have what's called a single, this is kind of marketing, right? Single pane of glass for management. Meaning that when we want to manage all of our access points, and let's just say, obviously I don't want to draw this out, there could be like 15 access points on one floor. This could be 12 access points on this floor and 20 access points on another floor. Maybe that floor is more dense with more things that can cause like refraction and interference, okay? So, and then, this is our first floor switch, second floor switch, third switch, okay? So the switch is going to connect to those access points, PoE typically, and this access point is going to connect back to this wireless LAN controller. Now, we're not going to deep dive on how it connects. There's 5 different ways a LAP can connect to a wireless LAN controller. DHCP, DNS queries, a lot of different ways, right? But what's going to happen is this lightweight access point is going to create 2 tunnels that are going to directly connect it to this wireless LAN controller, obviously through our wired backbone. But this is like a tunneling technology. It's called CapWAP, okay? They're going to create 2 CapWAP tunnels. I'm going to draw this in purple. The first CapWAP tunnel, and every single access point is doing this, is going to be a control CapWAP tunnel. Okay? That control tunnel is going to be what this wireless LAN controller does to manage that device. It is going to update, send profiles, add new wireless networks to that lightweight access point through the control CapWAP tunnel. Now, this could be anything. Let's say we have, let's do this color. Let's say we have VLAN 10, which is the 10.0.0.0/24 network. And we have VLAN 20, which is the 10.10.0.0/24 network. Well, since we have that network segmentation, VLANs in our regular switch network, we need to propagate that to our wireless network. So we're going to have 2 SSIDs, 2 wireless profiles that are going to match, that are going to correspond to these networks here. So we're going to have 2 wireless networks represented by 2 SSIDs that are broadcasted by all these access points. We do all that configuration from the wireless LAN controller, okay? So all these access points, and if we enable things like 802.11r, roaming, they're going to be broadcasting all the same SSIDs that correlate back to a wireless network in this subnet and that broadcast domain. So that is lightweight access points, okay? That's obviously going to be for robust. When you go to the airport, and you go to the Delta Lounge, this is the setup they have. They have lightweight access points that are controlled by a wireless LAN controller that's configuring all those access points. Now, the base functionality is still there. When we're talking layer 2, encryption, right? We're talking like WPA3, SAE encryption. That's all happening at the access point. That's determined, right, by the wireless LAN controller. It's going to tell it what kind of encryption to use, right? What SSIDs to broadcast and things like that. But the access point still has radio antennas in there emitting Wi-Fi signals for Wi-Fi enabled devices to connect to. Okay, I think that's going to cover it for lightweight access points. Oh, sorry. So that's the control CapWAP tunnel. I knew I was forgetting something. So now you may be wondering, what about the users? So when I have, let's say, a user connecting to the SSID VLAN 20, so user part of VLAN 20, and it sends traffic. Let's say it wants to send traffic in a standard configuration to another user sitting on the same access point. Well, guess what? We're going to build another CapWAP tunnel that's just for data. So we're going to have a data CapWAP tunnel as well. And yes, even in a standard configuration, when these 2 devices talk to each other, guess what? Their traffic is going to be tunneled through that data CapWAP tunnel, where then the wireless LAN controller is going to decide how to forward that traffic, how to direct that traffic, okay? So that is lightweight access points, as simple as I can make it. There's obviously multiple different ways we can deploy this, but that's as simple as I can make it. Okay, and now to touch on Cloudbase, just real quick. Cloudbase does the exact same thing. I'm just going to write it up here. It's almost identical deployments, but guess where that wireless LAN controller is? It's in a CSP now. It's in a cloud service provider, okay? It is just being managed now in a cloud-based solution. Something like Cisco Meraki, where we go on our Meraki dashboards, which again is accessed via the internet, part of the NIST standards of what makes a cloud solution, right? What makes cloud computing is that your resource, your portal, your console can be accessed anywhere you have internet, right? So that's what a cloud-based access point is. The access point doesn't live in the cloud, no. It's just getting controlled from a cloud controller rather than a wireless LAN controller that may be sitting on-prem here, okay? All right. Now, last thing we're going to talk about with network components is an SDN controller, okay? So we have a whole section on this, so I'm going to go through this quickly. But what is SDN, software-defined networking? So software-defined networking takes a step, is the next evolution, right? Which is actually just more the standard now of networking in typical big enterprises, different from traditional networking. Where traditional networking, so if we write up here, traditional versus SDN, is we're going to have all of our devices here connected, let's just say, okay? And if we want to configure, manage, troubleshoot this device, we have to either console into it or we SSH into it using a terminal emulation program like Secure CRT. And then we manage it one by one. In traditional networks, we have this network device has different planes. One is the control plane, one's the data plane. The data plane is going to be all that traffic coming on the wire, right? The actual packets coming inbound, outbound from that network component, that network infrastructure. That's the data plane, right? The control plane is all the technologies and protocols we configure to help us direct and route and switch traffic. These are things like routing protocols. Things like CDP are considered control plane traffic. If I configure a GRE tunnel, right? The technology, GRE, the technology IPsec is a control plane protocol. We have another plane called the management plane, where the thing allowing SSH, the VTY lines that are allowing remote terminal sessions or connections, that's the management plane. If I configure SNMP, that's going to be part of the management plane. So, long story short, a traditional network, the data plane and the control plane are both located at that device. Now with SDN, we have two major solutions in Cisco. We have SD-WAN, and this is talking for the enterprise. Yes, Meraki's always kind of been an SDN solution. We're talking enterprise level, though. And then we have SD-Access. And the actual component here, the server enabling SD-Access, is going to be something called Catalyst Center, which used to be called DNA Center. That's the old WAN. Now it's called Catalyst Center. With SDN, that control plane is centralized. So SDN, let's just say we have our DNA center here. Or sorry, our Catalyst Center. I'm just going to call this CC for Catalyst Center. We can split this into two regions, I guess you'd call it. We'll call it northbound, southbound. So beneath this controller is going to be all of our physical network components. Switches, routers, firewalls, access points, okay? We're going to call this southbound. And that controller is going to manage, configure, and troubleshoot all of our network infrastructure using like southbound APIs. That essentially can be anything. From your Catalyst Center, you could do a CLI command down. You can do SNMP. You can do netconf. You can do restconf, okay? You could use NSO to control, manage, deploy what we would call the southbound, but also we'd call this the fabric underlay. And then we have above the controller, which is going to be us. Us using REST APIs, accessing the GUI to actually configure that controller to manage all this fabric underlay. We'll call this northbound. We can use northbound APIs like REST APIs, right, to gather information or to set configuration. And we'll also call this the overlay when it's north, right? Northbound. We'll call this the overlay, all right? So the main takeaway from this is no longer are we in the CLI to manage. If I have 500 switches and I need to make a change, I need to do like a code change, right, on 500 switches. I can have consistency and I can make code changes, configuration changes, all from another single pane of glass. Very similar to how wireless LAN controllers have always done things in wireless, but now we take that a step further to our entire enterprise, okay? So that is SDN, software-defined networking. All right. I think that's going to be it for network components. Let's go ahead and take an 8-minute break here. Come back at 5:40 EST, and then we'll jump into hardware components, pretty much going over the boot process, and then network architecture. Okay, let's go ahead and now go over... Alright, let's go ahead now and go over hardware components in Cisco. So what we're going to talk about really here is just the boot process. The boot process of a typical Cisco router. What's actually, the meat and potatoes of a router. So in Cisco, this is going to be our boot process. And as we go through this boot process, if you've taken A+ before or really know anything about how computers boot, you're going to see things that are pretty similar, okay? So a Cisco router switch follows these boot up steps. First, we have something called a post test. This is much like a BIOS check of a computer. A post test looks at the motherboard of a router or switch and says, okay, does my input and output of my hardware work? That's our post test. It's the first thing it does on boot. So first we have a post test. And again, that's going to check, I'm going to type this out. That's going to check the input / outputs of the hardware of your switch or your router. Okay. Next, I'm actually going to type all this. It's going to be ROM, which is going to be, it's going to, after the post test, boot into something called read-only mode. So when you get in that read-only mode, that's kind of like the step before it actually starts loading the operating system. So during ROM, we're going to load the bootstrap program, is what it's called. The bootstrap program. And once we load that bootstrap program, it's going to do one thing, and that's going to search for an iOS. So when we say search for an iOS, we're not talking Apple, we mean the Cisco operating system. So it's going to search for iOS. Now, there's a couple different ways to search. One, the first thing it's going to do is check flash. Flash is going to be the storage of your router or switch. Much like a hard drive or a solid state drive or an NVMe drive is a storage for your desktop and laptop. That's what flash is for a Cisco device, okay? So it's going to search the flash for a good iOS, a good operating system stored there, much like the Windows operating system is stored in the C drive, which is just, again, your hard drive. If there's not a good operating system in flash, it's going to start sending a broadcast out, but it's going to be TFTP, right? It's going to say, hey, to all IP addresses, I'm searching for an iOS, okay? If it can't find that, it's going to load into ROM-on mode, which is almost like sitting at the BIOS menu, right? In ROM-on mode, if we ever reach it, there's not much you can do. Again, it's literally like sitting at the BIOS, almost like sitting at the BIOS menu of a computer, okay? From there, we can try to load an iOS, boot into an iOS. We know there's one at the flash, and it just didn't find it because it's corrupted, whatever the case may be, right? We can also do password recovery from ROM-on mode. So we're going to get into that in just a second. Next. Actually, let me go in here. I want to bold this so we know that's the steps. Because I'm going to be able to share this whiteboard with you after. We're supposed to have another student here, but he's in the Army. And he's like, we're doing, like, it's like we got cyclic inventories. I don't know. But anyways, he said he'll watch the recordings. Next, we're going to boot into the flash, okay? Now, this is where we find a good iOS in the flash. And now so we start booting the operating system. And in the flash, we're going to look for NVRAM, okay? So what is NVRAM? NVRAM is what we call the startup config. So the flash is just like a hard drive. And just like you have a C drive, that is your Windows operating system, right? And then in that C drive, you have like users. You have Windows, and then whatever the case may be, right? Documents, downloads, desktop, right? All those different folders and files. In the flash, we have other files too besides just the operating system that lives there. The NVRAM is just a file that, when populated, when saved, when configured, is also our startup config. So once we boot into the flash, now we're looking for a startup config, okay? So the NVRAM is, again, that startup config of the router or the switch. If there is NVRAM there, or if there isn't, actually doesn't matter, the next step is we go into RAM. So RAM is, guess what? This is the running config. So this is when we go on PuTTY, go on Secure Sierra T, our terminal emulation program, and we get into the CLI of a router or switch, this is the RAM, okay? The running config. These are where changes are made. This is where all of our caches are. So MAC address table, ARP cache, routing table, okay? That is the RAM. So the boot process goes exactly like this. First our post test, then into read-only mode. And in that read-only mode, we're going to load the Bootstrap program. We're going to search for an iOS. If we don't find a good iOS, we're going to go into ROM-on mode, just like the BIOS menu. If we found a good iOS in the Flash, we're going to now look for a startup config, okay? And if there is a startup config, we're going to load that into RAM, into our running config. If there is no NVRAM, we just kind of skip this, right? And instead of loading NVRAM, we just go straight into the running config. So I talked about password recovery on a Cisco device. So if you're, let's say, on site, network engineer quit, you can't get into the switch because he or she made a crazy password before they got fired, and now you need to do password recovery on that switch. Well, what you can do is reboot the switch, do a break sequence, or hold down the mode button on a switch on the front, boot you into ROM-on mode, and from ROM-on mode, you can say, hey, confrag 0x2142, and that's going to tell this, hey, don't do your normal boot process where you look for NVRAM, just go straight into RAM, and then you make your changes, and then you save it, and then you get new startup configs. That's what password recovery essentially does, okay? You do that from ROM-on mode if you want to do password recovery from the router or switch. Okay, awesome. So that is our hardware component, that is our hardware components. Now let's move on to our network topologies. Now we're going to go over some basic vocabulary and some basic network topologies, okay? So the first thing we're going to talk about is the LAN. So a local area network. Local area network. So this is a collection of devices that are physically in one location, and they're going to share a broadcast domain, okay? So a LAN is going to share a broadcast domain. And what we mean by that is that if we have a switch here, just like back in the day, right? LAN parties on like Xbox. I don't know how old you are, man, but yeah, I used to do that, you know? LAN parties at my buddy's house. That's exactly what it was. We all got our Xboxes or our PlayStations, hooked it up to a little Netgear switch that we had our parents buy from Best Buy or Fry's Electronics back in the day. And then we all hooked them up and we were able to all play together in multiplayer on our own devices. That's what a LAN is today still. It's just devices connected here. Let's say we're all on the 192.168.0.0/24 network. And this is our LAN. This is our broadcast domain, this network or sub-network, okay? Now, we usually say it like, oh, it's on the LAN. That's going to be at a physical site, right? Like, if we're in a big enterprise, we work at the headquarters. We have like 50 to 100 out sites. We're going to say, oh, yeah, like their LAN has a problem or something like that, right? Typically describing a small office. Now, we have that big 12 stories campus network. We sometimes use LAN, right? But in there, we have so many different VLANs and broadcast domains, campus network. But anyways, okay, next is WAN. So WAN, this stands for Wide Area Network. And this is going to be any connection that connects us to another network, okay? A lot of times people think that this means, oh, my internet connection, which is true. Your connection from router to ISP is considered a WAN connection, but a WAN connection can look like this. A WAN connection can be router to router, and this actual serial interface here, or whatever it is, gig, it actually doesn't matter. That's a WAN interface. Now, why? Because each router here is going to have its own LANs that we want to get connected to. So we're going to have our own LANs that we want to talk to, right? And in between here, we have a WAN connection. A WAN connection can look like this. Out to the ISP. And that's a wide area network, okay? If we have another router over here, That's also a WAN connection, okay? So that's what a WAN is, a wide area network. Next, let's talk about something called a SOHO, okay? SOHO, this is going to be small office, home office. So SOHO stands for small office / home office. So it's exactly in the words, right? Small office, home office. Small office, home office is just a single broadband connection, okay? So they're simplistic, they're cheap, their availability for the customer. When you go to your local ISP, that's what you get, a small office, home office network. So they enable multiple users to share a single broadband connection. So in a SOHO, this is just, right, that ISP connection to like your modem. That's a modem. And then to like your autonomous access point, your wireless router that does the routing, the switching, the firewall, the DHCP server, right? But what do we need to know about this is that it's a single broadband connection. So that's SOHO. Now getting into the bigger topologies, now we're going to touch on something called the 3-tier core topology. The 3-tier core topology. This is Cisco's campus network. It's big campus networks. And really when we look at enterprise, right, we look at enterprise solutions from Cisco, we're looking at the Catalyst series. We have access switches, distro switches, and core switches that they sell you, right? So it kind of, it falls in line. So the 3-tier core topology, here's what it looks like. So we're going to have 3 layers of different devices, different switching devices. So we have the core layer, which is going to be our most robust switching platforms. We're not going to connect endpoints to here. Most of the time, this may be 10, 40 gigabit uplinks. It's going to be robust backbone connections to the internet or to the ISP, or maybe to like a core router, like an ASR platform. But we're going to have our core layer. Okay, so this is core layer. So this is going to be the biggest and fastest devices that aggregate all traffic towards the internet. It's the backbone of your infrastructure. Now, of course, if we're going to have more than just one interface here, we could have 4 interfaces here. But then connected to that core layer is also going to be some big, beefy multi-layer switches, probably Catalyst 9400, 9500 series. This is going to be the distribution layer. I always say distro layer, and I got called out on it one time. Like, actually, on the test, they may call it distribution layer. So, okay, distribution layer, okay? This is the distribution layer. So at the distro layer, one, this connects our users to the core layer, so it's the in-between, but it's going to provide all that policy-based routing for all of our internal traffic. Meaning, at this distro layer, we're going to have switch virtual interfaces that are going to be the default gateways for all of our VLANs and users. We're going to have ACLs here. We're going to have our routing here as well. We may have a routing protocol enabled on these interfaces out towards the core, okay? So ACLs for filtering, all of our subnets, all of our VLANs. Connected to here would be like the on-prem quote-unquote data center. Now, obviously, if we have an actual data center, that's data center technologies. But if we have servers that support our HQ or our little spoke, right, we usually connect our server farms to the distro layer as well, okay? That's also going to be like an ether channel there. We're going to have link aggregation there as well, okay? So that is the distribution layer. Let me just make this look a little bit better. Okay. Next, we're going to have the access layer. And that's the last layer that's going to connect all of our endpoints, all of our devices, printers, VTCs, phones, users, and access points. So then we have the access layer. And this is how we draw the access layer switches, okay? This is going to be sitting in our IDFs, or intermediary distribution closets, our comms closets, right? That are going to be supporting all the users and all the different endpoints that we may have. And yes, we're going to have some redundancy like this here, okay? So again, this is going to be what all of our endpoints are connected to. Printers, VoIP, the access layer. So it's going to be like Catalyst 9200, Catalyst 9300 series. And these are typically going to be layer 2 switches. Now, I have seen, though, and I've worked in enterprises where sometimes our access switches can do routing, though. Like, we may have like a layer 3 point-to-point connection from an access switch to that distro switch sometimes, but typically they're layer 2. And the only SVI you'll have on here is like the management SVI. So that is our 3-tier core topology. Next, we're going to have the collapse core. We're going to have the collapse core topology. Now, with the collapse core, hold on, sorry, real quick. Okay, so on the collapse core, we're just going to combine the core and distribution layer, okay? So we're just going to combine them. So we're going to have 2 layers here. And before I move on, for the 3-tier, things you need to know for the exam, or just some basic facts that they may ask in an exam environment. It's large. It's for growing enterprises. With the collapse core, this is for small, medium-sized businesses. Not offices, businesses, okay? Which have minimal growth. But yes, the core and distribution layers are combined. So pretty much what we had in the core and distro layers, now we have it combined. So this is the internet backbone, and it's still doing all the routing, policies, ACL, subnets, and VLANs. Then the access layer, it doesn't change. It is still the access layer. All right, awesome. The next one we're going to talk about is something called a spine and leaf topology. A spine. Sometimes I don't know how to spell. There we go. A spine and leaf topology. Now, the spine and leaf topology, we have a couple things we want to keep in mind. We're going to have the spine switches and the leaf switches. You can kind of think of the spine switches as our more robust, high throughput, high bandwidth switches that are supporting our leaf switches. And the reason we want this topology is for like our fabric underlays, our SDN solutions, because they're going to provide us with consistent latency, and it also gets rid of the need for spanning tree. So another key point is that spine and leaf architecture devices are separated by the same number of hops as well. Okay, so I'm going to post some of these bullet points over here, and I'm going to draw what a spine and leaf topology may look like. So in spine and leaf architecture, devices are separated by the same number of hops. And spine and leaf architecture is a full mesh of leaf switches that provide layers of redundancy. So in that spine and leaf topology, let me move these a little closer here. We're going to have those spine switches. And then we're going to have all of our leaf switches. And these leaf switches all have a connection to every single spine. So the way it's going to look is kind of crazy. Let me finish drawing these out. Is going to be a connection to every single spine switch. So what does this create? That means every leaf switch is always one hop away from each other. If this is access switch 6 and this is access, or no, this would be leaf switch, right? So I'll do this. Leaf switch 6, leaf switch 1, no matter what, they're always one hop away from each other through the spine, because we can communicate either to this switch and back down or to this switch and back down. So always one hop away, and this gives us consistent latency. Okay, so that's going to be it for our network topologies. Now we're going to touch on the control plane versus data plane again real quick, and then we'll move on to, we'll probably take a break and go over, let's go over control plane versus data plane. We'll touch on the OSI model. That one I might bring up slides because I got some good images there. We'll take a break, and then we're going to get into IP addressing, which will be all on the whiteboard. And your homework tonight, man, will be to watch subnetting videos, because I don't want to take up 2 hours in this session. It's important, but during the IP addressing, I'll hit enough to get us, to get us through it, to get you to be able to do practice questions and things like that. Okay, where are we at? So control and data plane. Yeah, because I want to get you to some labs today too. I just feel so, if I don't get hands-on, I'm just like, what are we doing here? This is Cisco test, right? We need hands-on some Cisco shit. Okay, so control versus data plane. And also, like, we got to touch on IPv6, which is, pain in the ass. So, I got to get through that today, too. All right, so control versus data plane. So, the control plane, this is going to be where all of our technologies are that help us route traffic. So, in a controller-based network versus traditional network. Remember, in a traditional network, let's say this is our switch here, and I'm just not drawing a real switch, just like an overview of one. This switch right here in a traditional network would have the control plane and the data plane. That control plane would consist of technologies like Cisco Discovery Protocol, the Dynamic Trunking Protocol, and then like VTP, the VLAN Trunking Protocol. That would help us propagate VLANs. A router would have the same thing. A router would have that control plane local on it, and also the data plane local. And its control plane would be all routing protocols and things that help it forward traffic. Routing protocols, creating routing tables in there. Now, that data plane is just the inbound and outbound. That's where the forwarding table is going to live. So the data plane is going to be the forwarding table for both of these. So what do we mean by that? Okay. So traditional network, I'm going to write it up here. So let's just take routers, for example. Let's say I have this router, and let's break it up. So I have the control plane up here. Okay. I'm just going to call this the control plane. And let's say this router has OSPF enabled, and I have two interfaces here. Gig 00, gig 01. And I have an incoming packet. An incoming packet. So the control plane, I'm going to have OSPF running on that router. OSPF is going to create a neighbor table, and it's going to create a link state database. We're going to learn about all this. And those two tables are going to determine the best routes that go into my global routing table. And I had to go in here as an admin and configure that control plane traffic, okay? But then, what's actually happening at that incoming packet? Because I get that. I get we configured OSPF. It's a technology that the router is running that builds our routing table, essentially, that tells us how to route traffic. Well, the control plane, that routing table, is going to inform the data plane, our actual forwarding table that's switching traffic through that device, incoming on an interface and outgoing on an interface. So then we have our data plane here. And that data plane is going to be what's called the forwarding table. That forwarding table could be something like Cisco Express forwarding or process switching. But in that forwarding table, what it's going to look like, I'm going to zoom over here, is right incoming, outgoing, gig 00, gig 01. Is in that forwarding table. We're not going to have a routing table with, oh, here's how we learn this route, here's its metric, yada, yada. It's just going to be read the destination IP, boom, forward it out here. So it'll say, okay, we got this information from our routing table. If it's a catch-all, send it out gig 01. That's what our forwarding table will look like. Just something simple like that. All right, if you're talking to 110/24, go out serial 00. That's all the forwarding table looks like. It's for fast switching, okay? So that's the data plane. That's the control plane of a router. Now, in controller-based networking, we take all this control plane shit, and push it to an SDN controller that's going to centralize that process. All right, cool. So let's move on. I don't want to take too much of that time. We'll keep going over this. All right, next, let's go over the OSI model. And yeah, I think I'm just going to show the slide for this one because I got some good shit on here. So let me share this. Okay, OSI model. So the OSI model is going to describe how we encapsulate and de-encapsulate in computer networks. So you can see our data encapsulation starts when I send an email, and that application is through Exchange, and then I get encapsulated all the way down to the physical layer where I'm going to become like analog maybe on like a copper wire that then's going to get digitized on the other side and re-encapsulated all the way back up to the application. So OSI model has 7 layers. Layer 1 is physical, or going a little too fast here. For network engineers, we typically do our troubleshooting between layers 1 and layer 4. Now, it doesn't mean we don't give a crap about layers 5 through 7 because the session layer is important for managing our sockets. That's where APIs are, managing encryption, things like that, TLS. But typically, we just want to make sure that packets are reaching end to end, right? That's like our main goal. So let's go over layers 1 through 4. So layer 1, where most troubleshooting begins, that's going to be anything that directly connects devices. That includes Wi-Fi as well. Wi-Fi technically is layer 1. Like the actual RF being emitted is layer 1. Okay, so layer 1, we have copper, we have fiber, and we have Wi-Fi. In copper, we have coax cable that can be used to deliver TV, internet, things like that into our home or small office. And then we have what we call Ethernet cable with our different categories. These different categories are going to determine, that's Cat 5 through like Cat 8, the different speed and the distance. And then the actual copper wiring in there, we have 2 different versions as well. We have unshielded twisted pair and shielded twisted pair. With unshielded twisted pair, our copper pairs are not protected and can be vulnerable to things like EMI, crosstalk. And then we have shielded twisted pair, which is going to have an aluminum foil wrapping that's going to shield our copper wires from that EMI and any interference, okay? Then we have fiber, which comes in 2 different modes, multi-mode and single mode. With multi-mode fiber, we're going to have a bigger glass core, about 50 microns or like 62.5 microns in size, and we're going to have multiple streams of light that are bouncing along that glass core. And that glass core, and with multi-mode, we're not going to have as much distance, maybe up to 550 meters. Multi-mode is typically going to be used in like our data centers, our campus networks, and patch panels local to us. And then we have single mode. Single mode is going to have a smaller glass core of about 9 microns, and it's going to have a single stream of light going through it. This is going to be for distance, for long-haul communications. Now with fiber, we have multiple connector types. That it just depends. And when we plug in SFPs, we're going to have to know the different connector types and different types of fiber as well. Here we have the four, I guess, basic ones: LC, SC, FC, ST. I don't expect you to memorize all of them. With our copper cables over here, our Cat5 standards, our Ethernet standards, we're going to use what's called RJ45 jacks for typical basic Cat5, Cat5e, Cat6. And we're going to have a couple different wiring standards. One is called T568 Alpha. Another terminating standard, is T568 Bravo. You can see our copper wires here are going to be color coordinated. And on the screen here, we have the T568 Bravo standard with orange, white, orange, green, white, blue, blue, white, green, brown, white, brown. And you can see here with our different Ethernet speeds, we have Ethernet, which is 10 megabits per second. We have fast Ethernet, which is 100 megabits per second. We have gigabit, which is then 1,000 megabits per second. And you can see here when we get up to 1,000 megabits, all four pairs, 8 pins are going to be used. But with Ethernet and fast Ethernet, only pairs 1 and 2 and 3 and 6 will be transmitting and receiving. Couple that with PoE, we need all 4 pins, all 4 pairs, all 8 pins to actually be working for a lot of our PoE standards as well, which deliver wattage and power to PoE-enabled devices like cameras, phones, and access points. Okay, then layer 2, we kind of went over this day 1 pretty heavy. Layer 2 is switching. It's MAC addresses. It's what we call frames. When we create a layer 2 frame or packet, we call it a frame, right? A switch is a layer 2 device that will forward frames based on their destination MAC. Layer 3 is all going to be IP addressing. It's going to be routers, routing IP addressing from end to end. And then layer 4. So layer 4 is the transport layer, and this is going to be going over TCP and UDP. TCP and UDP are our transport protocols that are used to deliver traffic end to end. TCP, we have something called a three-way handshake that's going to deliver a TCP data channel that is reliable. It ensures that every single byte in that packet reaches end to end. With UDP, that's going to be a connectionless protocol that we consider unreliable. What we really mean by that is we use UDP for live streaming, video, voice call, where we can have some packet loss without actually restarting that connection or session. So with layer 4 or TCP, that three-way handshake, it's going to look a little something like this. I'm going to show my whiteboard now. So with that TCP three-way handshake, we're going to have, I'm going to draw this out here, a sender. Otherwise known as the client in a client-server architecture. I drew a server though. I need to draw a client. Let's draw a computer. And then we're going to have our receiver. Now, yes, a server can be a sender too, right? But this is just a typical client-server web architecture. When the client wants to establish an HTTP, wants to go to a website, HTTPS, Trepatech.com. Before we get to that hypertext transfer protocol, we have to establish a TCP session. Really more accurately, a TCP data channel to actually do that hypertext transfer protocol. When we establish that TCP connection, the first step is going to be sending what's called a SYN flag. So in that layer 4 header, we're going to have TCP flags. A FIN flag, a SYN flag, an ACK flag. That SYN flag is telling that server, I want to initiate a connection to you, a TCP connection to you. Step 2 is that server is also going to send a SYN flag telling the client, yes, I want to start a TCP session with you. But it's also going to send back an acknowledgement flag as well, saying I acknowledge your SYN and we can be connected. And then step 3 is we're going to send back an acknowledgement flag saying I acknowledge your SYN. Now let's establish our TCP data channel. Now, why do this? Why not just start sending? Because in that TCP data channel, let's say we're sending 1 megabits per second upload to that server, or let's say we're requesting, doing an HTTP request to download a, 30 megabit file, or just going to like a website. We want to get all the information on that website. The reason we have this TCP data channel is because TCP, during this connection, whether we're uploading, downloading, accessing a website that's displaying the HTML and CSS on our web browser like Chrome, we want to make sure we get all the information. We want to make sure that the packets coming across here, remember, we could be in like Arizona, this server could be located in New York with no content delivery networks involved. We could be connecting to a server in New York through multiple ISP hops. We want to make sure that we get all the packets so we can see everything on that website without any missing information or any files or things we download, okay? Well, because of that, during that TCP connection, we're constantly sending these SYN and acknowledgement flags in the layer 4 header to make sure that all the packets are being delivered. So let's say this is 1 second and this is our like speed or like our bandwidth. So let's say this is 20 megabits. Let's say during that TCP connection, we're downloading things at 10, 15, then we hit 20 megabits per second, and then we start noticing packet loss. Well, TCP is going to recognize that packet loss, and it's going to say, hey, we need to restart that session again. So that's in my office building here, okay? Another key note is that this is always unicast. So this is always 1 to 1. So this is the TCP three-way handshake. All right, cool. I'm going to go ahead and take a 12-minute break here. We'll come back at 6:30 EST. I'm going to jump into IP addressing, IPv6 addressing, and then we'll go over some hands on the keyboard, going over the basic CLI stuff. And then we're going to do a quick session of VLANs, and I'm going to have you do your first lab, man. How to figure out how to fucking open up the live chat here. Hold on. Okay, let's go to this live chat. She don't believe in shooting cars. I need to mute this. I'm gonna get some crazy shit. Pop out chat. Go back to OBS. Add a scene. Chat box. What the fuck is this? Browser. Here we go. Oh shit, this is dope. Damn, I can't see shit though. Yeah, but how the fuck do I interact with this shit? Now, there was a way to do it. Chat overlay. I want to do chat overlay. It used to come up here on the right. I don't know what the fuck happened, but this is gonna be like too much in the screen. Yeah. Yeah, fuck it. I don't need the chat. I'll figure this out later. All right, let's go over IP addressing now. So I'm gonna try to keep this like, I'm gonna try to keep it as brief as possible. But let's just go ahead and let's get some nice space up in here. So IPv4 addressing. So what is IPv4? I'm gonna make this black actually. Let me fix this real quick. Hold on one second. I'm gonna fix my pen pad here. There we go. All right, bet. Okay. All right, so what is an IPv4 address? So an IPv4 address is a 32-bit address. Let me type this out. An IPv4 address. 32-bit address that identifies a device on the network. Makes it unique, right? Gives it a unique address. Gives devices a unique address that is used to communicate on a computer network. Now, we say 32-bit addresses. What we mean by that is 32 bits, that's ones and zeros. So binary is the language of computers. Computers speak in machine language, which is binary. So we say 32-bit address. That can also be categorized as 4 bytes because there's going to be 8 bits in a single byte. We can also write an IPv4 address as dotted decimal, okay? So when we look at it in the binary form, this is how an IP address is going to look. It's going to be like 11110000 dot 11000000 dot 1111111 dot 01001100. That's the binary form, right? The dotted decimal form, we convert that binary into whole numbers 0 through 255. Off the top of my head, I don't know what that actually converts to, but it'll be something between 0 and 255, dot 0 through 255, dot 0 through 255, dot 0 through 255. We call this dotted decimal format. That's kind of how we read it as humans, right? In dotted decimal. So in dotted decimal, you're going to have 4 whole numbers, 0 to 255, separated by a period or a dot. We call this an octet. We call that an octet. Now remember the purpose of an IP address, an IPv4 address, is to identify a unique device. Give a device a unique address to communicate in a computer network. So when we look at this, 32 bits, that means 2 to the 32nd power, because binary operates in powers of 2, is how many total IPv4 addresses we can have in the world, okay? So 2 to the 32nd power. So if I bring out my calculator here, let's do that. Bring out my scientific calculator. 2 to the power of 32 is 4.2 billion. So 4.2 billion. So that means we can have 4.2 billion unique addresses for all of our computing devices that want to connect to the internet. Now, obviously, that's not enough nowadays, right? So we ran out of globally unique addresses a long time ago. And not right now, but we'll get into what we did to conserve that. It deals with something called class-full versus classless addressing, and then private IPs versus public IPs, and a technology called NAT. But for now, basics on IP addressing. So to dive into IP addressing, first thing we have to do is learn how to do this translation. How do we translate binary into dotted decimal? And how do we translate dotted decimal into binary? Or binary and decimal conversion. That's the first step to understanding IP addressing. Now, of course, we have our basic information written out here that you may need to know for the exam. 32 bits. It's unique. Octets, right? 0 to 255. And that's because we have 8 bits here, right? 8 bits. That's 2 to the 8th power. I don't know why I always mess up writing the number 8. But that's 2 to the 8th power. What is that? I got my calculator out here. It's 256, right? Another thing in computer networks is that 0 always counts as 1. So 2 to the 8th power. I need to rewrite that. That just looks awful. 2 to the 8th power. There we go. 2 to the 8th power, sorry, equals 256. But in computer networks, 0 counts as 1. So our range for each octet is still 0 to 255, which actually equals 256 because 0 always counts as 1. So if we were to, let me turn on my camera for you in the Zoom chat too. Hold on, can you see me? Hold on. Why can't you see my face in here? There we go. So if we were to count in binary with our hands, it would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So in binary, in computer networks, computer language, we only have 9 fingers, right? No, technically it's 10, but it starts at 0, 1, 2, 3, 4. And that's something you're going to have to, that's something we're going to have to, stop the video. That's something that's going to come up again in subnetting, okay? But now let's go over this binary to decimal conversion. So how do we convert binary to decimal? Well, first, we have to write out a chart. I call it the binary conversion chart. Binary conversion chart. And it's going to be all the powers of 2 up to 2 to the 8th power. Now, what I mean by that is, if we start at 1, 2, 4, 8, 16, 32, 64, and 128. This is our binary conversion chart here, okay? We're going to use this chart to convert binary to decimal and decimal back into binary. So using this chart, I'm going to erase this box here. Actually, I'm going to erase these numbers because I want to write them out. Actually, write them out. It'll be 128, 64. I don't know. I hate that it does that. 32, 16, 8, 4, 2, 1. I'm going to give myself a little bit more spaces here. I don't know. It gives a period. It's so annoying it does that. See? Chill. Okay. There we go. Dude, I hate that it does that shit. I mean, I guess it's nice. Maybe you're typing a fuck ton, but we doing like math over here. Okay. So here's our binary conversion chart. So now, let's do this thing. Another thing I forgot to mention is that the 1 bits equal on, and the zeros equals off, okay? 1s and 0s equals on and off bits. So when we get to subnetting, when we actually get to the subnet mask, the 1s equal the network bits and the 0s equal the host bits, but we'll get there, okay? All right, so the 1s. So let's say I have an IPv4 address here, 4 octets. So I'm going to have 101.0.1.1.0.0, that's 8 bits, dot 0.0.1.0.0.0 dot all 1s, the last bad boy there, and then all 0s except the last one there. So how do I convert this into decimal? Well, I'm going to take each octet individually, and now I'm going to line them up against our binary conversion chart. And here's what we're going to do. If it's an on bit, it's an on bit. So it means it's going to equal that number. If it's an off bit, that's 0. 32, 0, okay, 8, 4, then the rest are zeros. And then we're going to add that all up. So 128 plus 32 equals what? That should be an equals. That equals 160. And then we take 160 plus 8 equals 168. Then we take that 4, we do plus 4, that equals 172. So this first octet here is 172. Now let's do this one more time because I don't like beating a dead horse, right? Let's erase all this. Actually, easier way to do this. Just going to highlight all this. Okay. And now let's do our second octet here. We're going to do the exact same thing. We're going to just line those bad boys up. 0, 0, 0, 1, 0, 0, 0, 0. So this one's kind of easy. The only on bit we have is 16 here. So this is going to be 172.16. And that's how we do binary to decimal. Now let's do the opposite way. Let's do decimal to binary. So now let's say we have this IP address. Let's just make up a, I would say hard number, but 132.89.220.7. How do we convert this into binary? Well, now we're going to start above here. So we're going to write that number, 132. We're going to start off at each octet still. We're going to say, okay, 132. Does 128 go into 132? Yes, it does. Or another way to say it is 132 greater than or equal to 128? If it is greater than or equal to our binary conversion chart, it's an on bit. But that 128 takes away from it. It takes away from that 132. Okay? So now we're left with 4 because we do 132 minus 128. Now we're left with 4. Is 4 greater than or equal to 64? No, it is not. So it's an off bit. It's a 0 bit. Is 4 greater than or equal to 32? No, it is not. It's an off bit. Is 4 greater than or equal to 16? It sure isn't. That's an off bit. And I'm just going to keep going down the line. And then ding, ding, ding. Here we go, guys. Is 4 greater than or equal to 4? It's equal to. So what do we got here? Our last on bit. So 4 minus 4 equals what? 0. And 0 is not greater or equal to anything. So the rest are zeros. So to convert the number 132 into binary, that's how we did it using our binary conversion chart. And here's the 8 bits. 1, 0, 0, 0, 0, 1, 0, 0. There we go. We'll do this one more time and then we'll do this one more time. And then I'm not going to get into subnetting. So the last thing I'll talk about, that's pretty much it. I'm going to talk about that. And then I'm going to have you watch the subnetting videos, Jacob. Probably like maybe tomorrow morning because I want to get us into VLANs, okay, before time is up. Let me, real quick though, I'm gonna pause just for a second. I got to plug my computer in. Hold on. Okay, we're back. Okay. So now, let's convert the number 89. Erase some of this over here. Okay, so convert the number 89. We're going to do the same exact process. Right? 89 above here. Is 89 greater than or equal to 128? It's less than. So guess what? Off bit. Is 89 greater than or equal to 64? It's greater than. That's an on bit. Now, public math is really scary, but 89 minus 64, my brain is fried. I've been working all day and then I had to teach. So, you know what? We're going to use the calculator here. It's 25. Okay. Is 25 greater than or equal to 32? No, it is not. Off bit. Is 25 greater than or equal to 16? It is greater than. On bit. 25 minus 16 is 9, but just to make sure, yeah. Is 9 greater than or equal to 8? It's greater than. That's an on bit. 9 minus 8 is 1. 1 is less than 4. 1 is less than 2. But 1 is equal to 1, so there's our last on bit. So the number 89 is going to be 0, 1, 0, 1, 1, 0, 0, 1. And that's how we do binary conversion, okay? Now, I am going to quickly move on here to... Actually, let's go ahead. Let's take another 5-minute break. I want to review some things, just like shortly. We're going to go into IPv6. So let's come back at 6:55 East Coast time. We're just going to dive into IPv6. I'm going to go over the highlights that you need to know for the exam. And then I'm going to give you one additional video to watch. And then we're going to jump straight into VLANs, okay?